Okay, so thank you. So today I'm going to start talking about what the closed string invariants are before we get on to the open string invariants that are the main subject of the course. But I'll probably spend at least 1.5 talks, maybe 2 on this. So, you know, if I don't, when we finally meet them later, it will seem like we've put the cart before the horse. So it's best to do it now. Okay, so first let me tell you what structure we're going to try to see in the closed string invariants. It's part of the structure. So Gerstenhaber algebra. It's a graded vector space. Together with yes. Well, actually, in some versions it will have different grading groups. So let me leave it just as graded. We'll have different ground fields. Yeah. We'll see the ground field later in this talk, and we'll see why we're forced to use that ground field. So we'll have a graded associative algebra structure, which is supercommutative with respect to the grading. It's also going to have a super Lie algebra structure. So a Lie bracket. And actually for that, it turns out you need to shift the grading by 1. And these are compatible in the sense that bracket with any element A is a derivation of the product, the algebra structure for any A. Okay. Sorry? Here, it means the usual anti-commutativity of Lie bracket is actually up to some Cazul type signs. Similarly with the Jacobi identity.
Is the derivation for the associative product?
Yes. It's there's like 1 sign difference. Yes.
Except the bracket has a degree.
Yeah.
So implicitly the grading is either by Z or Z mod 2.
Yeah, it has Z2
It's
grading or Z grading?
You don't have a Z mod 7.
No, you don't have a Z mod 7 grading. There are, but basically, okay, the grading, as far as we'll be concerned, is Z or Z mod 2n. Although other things come up in this context. Okay. So this is the algebraic structure that the part of the closed string invariants we will be looking at will have. So I just wanted to say that at the start so that, you know, if you're not so into looking at complicated moduli spaces of holomorphic curves, you know, you have faith that something interesting will come out at the end of it. But today, we'll probably only see the associative algebra part of this structure. Okay. Oh, and yes, so I put this here to advertise Tim Perutz's talk on Friday because so part of the subject matter of that talk will be our joint work about this process of getting the closed string A model out of the open string A model. So, you know, if you're interested, you can go have a look at that. Okay, but now let me tell you what the closed string A model is, and I'm going to follow this really excellent set of lecture notes from Denis Auroux's graduate course on mirror symmetry, which are available on his website. Okay. So recall that A models had to do with symplectic invariants. So let M omega be a symplectic manifold. So this meant omega was a two-form, closed, non-degenerate. Let J be an almost complex structure on M. So the almost is because it's only a complex structure on the tangent bundle. It's not integrable, so we don't have local holomorphic coordinates. We say J is compatible with our symplectic form if when we combine them we get a Riemannian metric. And so to define our enclosed string A model, we're going to need to make a choice of such J, but space of such almost complex structures is contractible. So somehow this choice doesn't matter very much. So of course this is very different from making a choice of integrable complex structure on our manifold. Somehow very flexible and doesn't really matter. Now let sigma G be a Riemann surface, genus G. J is a complex structure on our Riemann surface, and it's equipped with K marked points, Z1 through ZK. Define the moduli space of such things up to biholomorphism, preserving marked points. And it's a complex orbifold of dimension equal to over complex numbers, 3g minus 3 plus k. So the orbifold, because some of these curves have automorphisms. This has a nice compactification, the Deligne-Mumford compactification. So this is a compact complex orbifold of the same dimension. And what this basically means is we include nodal Riemann surfaces. So for example, you might have some genus 2 curve with a bunch of marked points, and then another sphere bubbling off and a node at this point here, something like that. Okay. So if we have a map from our Riemann surface into M, we call it J holomorphic. If its differential respects the complex structures. So for any homology class, I'm going to define the moduli space of J holomorphic curves with this homology class modulo holomorphic reparametrization of the domain. Okay, that's what this one means. Now, these moduli spaces come in finite dimensional families. So basically to see why that is, we set up our functional analytic framework for dealing with these guys. We look at some, well, I should start down here.
So when you write bracket in your weakest bracket, you mean the image of the fundamental class? Or
Yes,
yeah.
yes.
Did you say what the tilde relation was?
Only in words. Tilde means holomorphic reparametrization of the domain. Okay, so maybe more explicitly I can say it here. We have two maps like this. They are equivalent if there exists a biholomorphism like this, preserving all the marked points such that this commutes. Okay. So we're going to look at maps from sigma into M of Sobolev class L plus 1 comma P. Together with a choice of complex structure on the domain of sigma, which is parameterized by this space here. And then we're going to look at the... Sorry?
Do I know what
It's
WLP
a-
is?
It's a Sobolev space, so it's a class of maps with a certain regularity. Okay, so it's you look at smooth maps from sigma into M. You put a certain norm on that, the WLP norm. So it's the sum of all LP norms of L derivatives up to order L plus 1 of the map. And then you take the Banach space completion. All I'm trying to explain is in what, how we show that these moduli spaces come in finite dimensional families.
When
And
you say common finite dimensional families, you mean it's a union of
it has,
components that are each finite dimensional,
yes,
but there are infinitely many components?
yes, that's right. I mean, yeah, the components are somehow indexed by the homology classes.
But beta's in the notation.
Okay.
So for each beta is finite dimensional?
Yeah. So maybe I should, yeah, you're right. I should just say that. You're right. So these moduli spaces are generically finite dimensional families, finite dimensional manifolds.
Generically in J?
Yes. Well, yeah, so we will, this is of course not strictly speaking true. This is a big technical aspect of the subject that we won't really touch on.
By generically manifold, you mean it's a space which has an open, which is a manifold?
I mean, for generic choice of J in the space, or the big infinite dimensional space of all almost complex structures compatible with the symplectic form in this sense, for generic such J, this holds. This space is a finite dimensional manifold.
What if you take M to the orthofold?
Yeah, okay. Okay. Orbifold, yes. Sorry, someone...
Said if you take a point, then already contradicts the first statement. Moduli space is an organ point.
Okay. Right, yeah. Okay, so...
Yeah, so technically that's only true if it has somewhere injective point, then that's true.
Yes.
Say that again?
If the curve is not multiply covered, then that statement is true. If you look at only the part of the things it's not multiply covered, you can arrange it by J. If the things are multiply covered, then that's not true.
Right. Yeah, there are... So... let's just say there are serious technical issues in making this hold in general. But for the purposes of what we're talking about, the kinds of manifolds we're talking about, one can do it without serious. I mean, okay, well, not in all genus. Yeah, there are serious technical issues, but let's ignore them for the
Generic
purposes.
is in rare category sense.
Yes.
Since we're interrupting, I was wondering, so in practice when this gets done, right, and papers get written, I mean, this sort of must occur. So I'd like to know if these Gromov-Witten invariants are defined in sort of the algebraic category, because my vague understanding is that in the purely algebraic category, I thought that Gromov-Witten invariants have been well defined for sort of a while now.
Yeah, yes.
And so,
That's my understanding too.
And so then, when these things are actually used, and since it's the case that you're working on Taylor manifolds anyway for this sort of near symmetry constructions, is it the case that this definition is just taken to be whatever sort of comes from algebraic geometry?
One can define it like that. So yeah, there are easier definitions of these moduli spaces in algebraic geometry world. The reason I'm framing it like this is that later on we want to talk about the Fukaya category, which does not have an algebrogeometric construction along those lines, and we want to relate that to these kinds of invariants, which requires us to be using the same kind of setup. Okay. Okay, so we have, sorry, I should have written sigma there. So we have this space of maps from sigma into our manifold, together with some bundle over it, which is the bundle of 1 forms on sigma with values in the pullback of the tangent bundle. And there is a section of this bundle called del bar j, where del bar j at u equals a factor of a half okay. So you can check this lies in this bundle up here. And when this section vanishes is exactly when this map is J holomorphic in the sense I defined up there. Yep. Right, so that is, so in our del bar equation, we have this little j appearing. And that little j is parameterized by points in here. MGK parameterizes complex structures on our genus G Riemann surface with k marked points. Okay. All right. So, this is an extremely rapid introduction to a very large subject, which we're going to skate over. So the linearization of this section up here is Fredholm, which means it has closed image and finite dimensional kernel and co-kernel. And its index is the dimension of the kernel minus the dimension of the co-kernel, can be computed topologically. So we'll call it 2D, and it's equal to twice the first Chern class of M, of the tangent bundle of M, evaluated on beta, plus these two terms, as it turns out.
What's that?
M is the manifold that N? N is the real dimension of our manifold is 2n. Okay. So if this section del bar j is transverse to the 0 section, which, as we were discussing, can sometimes be ensured for generic J. And of course, sometimes this cannot be ensured, and this is a subject that Helmut, is a world expert on, how to deal with that. So if this is not true, if this is true, then the vanishing locus of this section, so if it's transverse, that means this co-kernel should be trivial, and the index of our operator is just equal to the dimension of the kernel, which is locally the tangent space to the vanishing locus of this section. So in generic situations, we get this manifold of dimension equal to 2D, this index here.
Definition of 2D is right there.
Yes, this is exactly the definition. All right. Yes, sorry. So, we would like to use these manifolds, orbifolds, to define invariants of our symplectic manifold. So for example, if it's finite dimensional, if it's 0 dimensional, we can count the number of points it has.
Assuming it's compact.
Yes, assuming it's compact. So to do this, we need the moduli space to be compact. Okay. This is for two reasons, actually. So the count is finite. 2, so it's independent of J, which we kind of chose as an auxiliary choice to define these moduli spaces. So if we have two different almost complex structures, then to compare this count of points in two moduli spaces for different almost complex structures, we can look at a one-parameter family, and this might look like something like this. So over here, with J0, we have a bunch of J holomorphic curves with respect to J0. Over here, we have another bunch, And then we have some one-dimensional family. That wasn't very smart. Okay. That looks like this. And so the signed count of J0 holomorphic curves should be the same as the signed count of J1 holomorphic curves. Unless we had something like this. So that's clearly not going to give rise to the same count on both sides. So we need some argument why this moduli space we're defining here is compact for both of these reasons.
Is this the first place where you use the symplectic structure?
Well, we use the symplectic structure in our choice of which almost complex structures to look at, crucially.
In principle, you could define that space before, but if you want to get compactness, usually you need
Yeah.
omega because it controls area.
Yeah, that's true. So I guess we could define this without this condition. That would be completely fine. But yeah, when we try to prove this, we will not be able to prove any form of compactness if we don't have such a restriction on J. Yeah, that's a better answer.
So, all right, but a minute ago, J had to be chosen generically.
Yes.
And now if J0 and J1 have both been chosen generically, and you take this path, are you going to stay suitably generic in the whole path?
Right, so one has to choose this path generically as well. Well, up to the same qualifications we had over there.
But so, for instance, the contractibility of the space of J's is also holds for the space of good J's? Or
No, not necessarily, no.
So if you have J0 and J1 and different components of the good J's, and you choose a path which goes to the bad J's, do you get into trouble?
Yeah, but you're so much in trouble already.
But
The answer to your question is no, because he's drawn a picture precisely like that. I think, yeah, you know, you have some point already here where you have a t value for which J will not be generic in this picture.
yeah, I mean, but in situations where it works, you need to choose the path generically in the space of.
No, but for controlling the area, it's enough. It doesn't have to be a Riemann metric. You just need that omega is positive on complex lines. Then it's also there.
Okay, that's an
So
open
that
set.
means that you can actually wiggle around more. So
Right. Yeah, so I guess I'm hoping not to.
But the basic issue is to come up. I mean, because the spaces are not compact, so you have to compactify them. This moduli space are usually not compact, so you have to compactify them. To begin with, to get some kind of compactness, and then you get some kind of wider object, and then you want to turn it into orbifolds, which not always is possible. So then you have to come up with abstract calculations to achieve. And then you can just take something, any table J to connect it, and then you just have to abstract that to perturb and achieve what you want. But some things you have to go beyond this differential equation to perturb. You have to get this amount of input.
But even so, a generic path is different than, I mean, it's a larger class of objects. Exactly. So, I think that was somebody was asked.
So is it a case where this thing is not a manifold, but in the second dimension, how fast and then is miserably non-transverse?
It can be miserably non-transverse, but if you have a local notion of a dimension, you can argue that that dimension can't get too large a priori.
You can make a finite dimensional matrix, so you can represent it as a zero set of finite dimensional extension.
In finite dimensions, you need a priori bound. In terms of topology. You don't need, you fix a homology class and everything else, you don't need to go, you don't need to do a.
Are you sure?
Yeah, it basically boils down to sort of a generalization of automatic transversality.
But maybe for the purposes of this class, you know, we want to skate over this stuff. So, but this class, these lectures, whatever. Okay.
And is it clear that you can't have crossing of these things if it's not compact or something like this? Why can't these lines cross? Yeah. You sort of have
That is
air creation.
non-generic.
That's non-generic. Yeah, exactly.
Right.
So that could happen.
I mean, it's infinite-dimensional space. So, well, it could happen if false doesn't fit. I mean, without
But if you have a generic path, then it attacks the cross.
There's only a few things. Just keep writing on the board and make your class.
Okay, so yeah, maybe we'll keep going with Gromov compactness. So if we've got a J holomorphic curve, define its energy to be its symplectic area, which is also equal to the integral of the pullback of the symplectic form over this curve. And that's equal, and we have by our J holomorphic equation that by definition, when we evaluate this pullback of the symplectic form on a tangent vector together with its rotation by the...
you have to put the J in front. Because omega J something is...
Oh. Okay, so maybe I originally had it this way round, I guess. Okay. All I'm saying is that this the J holomorphic condition on our map means that when we pull the symplectic form back, we get something positive. So this energy is always greater than or equal to 0. With equality if and only if the tangent, this du of v, vanishes for all, you know, over the whole of sigma, so this map u is constant. Okay? Now, Gromov's compactness theorem says we have some sequence of J holomorphic curves. Let's just say genus 0.
So it's UI, not sigma. I mean, the sequences of maps, not of sigma staying the same.
No. Sigma I also can vary. I mean, sure, let's think of sigma I as always having the same genus, but the complex structure on sigma I could also be changing in this family. Okay. So what these stable maps look like. Very similar to what's in the Deligne-Mumford compactification. We have a bunch of J holomorphic spheres. So I said genus 0 to keep things simple. J holomorphic spheres together with nodes connecting them. And then your marked points that were part of your definition of your moduli space get carried along as well. But note you can have components of this thing that don't have any marked points on them. They're not stable in the usual sense of the word for the Deligne-Mumford compactification. I guess this is, all right, now it's not a linear tree.
But then this U infinity on those things has to be having positive energy.
Yes.
Is this a sequence of bounded energy?
Yeah.
Oh my goodness, yes, that is, okay. Yeah, that's a very important okay. Yeah, this is a sequence of J holomorphic maps with bounded energy. Then there's a subsequence that converges in this sense. Okay.
So convergence, I thought convergence meant in your Sobolev space. With the Sobolev space, all of the sigmas had to be the same.
It doesn't
No,
converge to Sobolev.
no,
The
it's
norms blow up, so that's also.
yeah, it's
So what norm or what space is it converging in?
what's the definition of the?
Which it turns out to be Hausdorff, which was also not even in Gromov's first paper. So Gromov defined a topology which was actually not Hausdorff, and Kontsevich observed that in 1988 that wasn't actually Hausdorff, so he added the stability condition to it, and then it became Hausdorff space. So it basically up to the things. So if you take the right number of points away, you can actually get the gradient bounded. So you take that. Suppose you fix on the sphere. So you just take sufficiently many points away and take the hyperbolic metric, and you actually can get gradient bounds. And then at the end you have to think how to fix it with points. So it's a little bit more complicated. You have to choose a pair.
So here's an example. You can think about this example of, this is a quadric. So this, for epsilon not equal to 0, this is just a CP1 sitting inside CP2 holomorphically. And in the limit, as epsilon goes to 0, this thing converges to some 2 copies of CP1 with a node connecting them. So, I mean, you can also, in a toric picture, it looks like this. So if you tried to, so what Helmut was saying is if you remove this point, I guess, and look at map from C, so CP1 minus with that point punctured, then on some compact subsets, including the origin, it's just going to converge to this guy here with this point punctured. And then you need to sort of zoom in and look at where this bubble came from by puncturing that point and show that things meet up like this. But basically think of this as the prototypical example of that kind of Gromov convergence.
So M is supposed to be CP2 here?
Yes. 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 So now we define the Gromov compactification. So it's sort of somewhat related to the Deligne-Mumford compactification. Okay, so now we define a new space which includes all these things that we saw as limits in the sense of Gromov compactness, of guys from our original moduli space. And okay, now you know, you hope, maybe I should say, this thing is a compact complex orbifold. So we've seen this this compactness. That's this result, and then of course there's a mess showing you really do have nice neighborhoods of points like this in your moduli space, but morally that's what you should think of this thing as looking like. Honestly, it's not always true. Yeah, but
We're outside Algebraic.
Actually, what you can achieve in more generality, what you can achieve is that it is locally written as a finite union of manifolds divided out by a group, which considers this, leaves this local union of manifolds in there.
If we're outside the algebra picture, where do we get the complex structure on the moduli space, assuming all the transversality elements?
okay. So yeah, you're absolutely right. This is not that's too much to ask for, really. Yeah, let's just say compact real orbifold. Yeah.
You're saying that the almost complex structure M doesn't even have to be an almost complex structure on this moduli space?
Sorry. No, it's that's not true. Well,
But it should have an orientation.
sorry.
Orientation.
Yes. So it is oriented. So it's got evaluation maps. So our curves came with these K marked points sitting on them. So we define the ith evaluation map of our curve to be evaluating the curve at this kth marked point. We also have a map which just remembers the domain of our curve.
Actually, it's a stable part of the domain.
Yes, so some of these guys here might not be stable spheres, and if that's the case, you have to collapse them in this map here. Okay. And now finally, define the Gromov-Witten invariants. So given k classes in the cohomology of our manifold and a class in the cohomology of m bar gk, I'm going to define this class sorry. Okay, sorry for running out of room. So we take this class psi in the cohomology of m bar gk, and we pull it back to our moduli space via this map S, which just remembers the domain. And we take all these classes alpha 1 through alpha k, we pull them back to our moduli space using these evaluation maps. We get some form on this moduli space, and we integrate it. And of course, this depends on having a nice structure on this manifold, and, you know, in general we don't. But this is the moral of what Gromov-Witten invariants are meant to be. So let me tell you another way of thinking about them.
Setup. So usually when the algebraic setup, you take a virtual fundamental class there. So the space is certainly not what you want. So you're saying you can construct the space to match the virtual fundamental class, or do you also have to do a virtual fundamental class construction here?
Yes, I mean, you certainly need to do a virtual fundamental class type construction here. I'm writing things that are, you know, that are not true because I want to try to explain what they're meant to be. But, you know, well, no one should go writing a paper saying that all this is true. Okay.
It looks like your thing actually realizes this class, right? Because the agreement then was a compact overflow.
Yeah, you can actually, this picture we just had before, that you can write it locally as a union of manifolds divided by group action, but you can actually triangulate the whole thing and so on. So you can actually make that.
So that
But it's a rational fundamental. I mean, you have to put weights and this kind of thing.
Okay.
That's possible.
But in your stuff, you wouldn't say you construct a virtual fundamental class. You actually construct
Of course, yeah.
a virtual one.
Well,
In your framework.
Well, I think
But I just said what one could do. I mean, it hasn't been done. But what has been done is that you can actually integrate over that. But you could actually triangulate. You take triangulate and push it forward.
Okay. So, morally equivalent if our class is a Poincare dual to some cycles, I should do a capital S to indicate it's not the same as the one from before. So if we choose cycles Poincare dual to all these guys, then what we're really counting with this invariant is the number of genus G J holomorphic curves in M meeting these cycles at the marked points. And with domain in this subset of our space of possible domains. Okay, so that's kind of a
Class beta.
yes in class beta. No, not necessarily. What we do know about the degrees is so. It's 0 unless the sum of these degrees is equal to this 2D that we defined a few boards ago. It was equal to this thing involving first Chern class of beta n minus 3 times 2 minus 2g. And k, right. The gradings of the cohomology classes. Degree, yes. Okay. So now we're going to try to combine all of these invariants over different homology classes beta into one invariant. So we're going to add them all up, multiplying by t to the omega of beta. So this is an element in a certain ring, which we call the Novikov ring. So let me tell you what it is. So that is the definition. The Novikov ring. And so you should think about it as being sort of like formal power series in T except that we have to allow non-integer powers for these lambda j to account for this omega of beta, this symplectic area of our class, which a priori might not be an integer. Although, of course, if the cohomology class of our symplectic form is integral, then we can actually work over this one. Okay. Sorry?
This is evaluation domain?
Yes. I think so. I mean, there's a valuation given by the the lowest non-vanishing power of lambda. Yeah. Non-vanishing lambda. Yeah.
So implicitly, there's some finiteness, finitely many betas with a given value of omega or something?
Yes.
That's a sum over betas, and this is a sum over.
Yes. So that is this thing here. The energy is omega of beta. And this thing here says that this is the space of J holomorphic curves with omega of beta bounded above is compact. So in particular, if it's a bunch of points, then it's finite.
There are only finitely many modular spaces.
No, the
Of
sum
this
over
energy
beta,
is-
the beta varies over a basis of the homology or over all homology classes?
Over all homology classes.
With coefficients, integer coefficients?
Integer coefficients, yes. I mean, this is the homology class of our curve.
Yeah.
So it's the homology class of some, yeah.
It's an H2 event, so it's lower two.
But below some energy, there are only finitely many where there's something happening.
Okay. So, and note here this, we're only looking at non-negative powers, and that's because J holomorphic curves have non-negative energy. That was this argument here. That's why we can use this analog of this rather than the analog of formal Laurent series. So yeah, so this Gromov compactness result is really crucial for us to be able to define our Gromov-Witten invariants over this ring by the argument I just said. You know, if we tried to, for example, substitute in some actual value of t, then there would be no reason for this sum to converge. I think it's expected to converge for very small values of t, but this is actually a really difficult problem because it says exactly how quickly these Gromov-Witten invariants grow, and that's difficult to work out. But
There's infinitely many beta with given.
yes, well, okay, I guess you can also define versions over more complicated coefficient rings, such as Q of H2 of M. You can just as easily do that. Well, and then you need to, wait, what's the actual correct? Yeah, and then you need to take some completion of this to allow infinite sums where the energy is growing arbitrarily. But you can define versions like this that keep track of the homology class of the curves that you're counting better. I guess
multiply these things.
Multiply.
I mean, in other words, the fact that it's a ring.
Yes.
Are you going to use that it's a ring?
Yes. Yes.
Which means you're going to multiply.
Yes. Yes.
That was the question.
Sure. Right. Oh, that was Richard's question? Or? No. No. Okay. That's.
What is the point of summing them by energy instead of keeping them separate?
I guess as far as Gromov-Witten invariants are concerned, there's no reason why you should lose that information. Later on, I'm going to talk about the Fukaya category, a structure that these guys fit into. And for those, we will not have such well-defined homology classes beta. Instead of counting closed surfaces, we'll be looking at arbitrary kind of Lagrange submanifolds of our thing, and we'll be counting holomorphic disks with boundary on these Lagrangians, and we'll be weighting those by their symplectic area. And there it becomes harder to separate things out into homology classes. You kind of only have this symplectic area that kind of makes sense to use. But for the moment, you could just as easily keep more information like that.
Is it obvious that if I fix a value of omega beta, so I just look at the ones where it's equal to 0, that there's only a finite number of non-zero terms of that particular G beta psi combination?
Yes, that is this result here. So omega of beta is the energy. And this result says that the set of all J holomorphic curves with energy bounded above by something is compact. In this case, we would be looking at, a compact zero manifold. So there's just a finite number of points that we're counting corresponding to curves with bounded energy.
Okay, so that just means that sum makes sense.
Yes, exactly. Yeah, this Gromov compactness is the reason why that sum makes sense. Yes. Okay. So
So in this compactness result, you have to control genus. So genus
yes. Yes. Yeah.
So Joe thinks maybe dimension 4, you could maybe get it down.
Integral currents, but not in Gromov.
Okay.
So far, the
But
genus hasn't been allowed to move.
right, I'm not summing over genus in that thing. Okay. So maybe I can say this here. So you should think of this T that appears in this Novikov ring as a coordinate on the moduli space of symplectic structures. Okay, which I spoke about last time. Okay, so maybe this is obvious, but I said last time that in our A model we wanted to sum over classes beta, the number of curves in class beta, e to the minus omega of beta, which, as I just explained, is very difficult to see if it's well defined. But of course, so t to the omega of beta is e to the minus log t omega of beta. So, sorry, e to the log t omega of beta. So we think of this as the large volume So we think about this as somehow parameterizing a family of symplectic forms which are kind of just the same two form but getting scaled up to infinity by this minus log t. So somehow this, so you should think about this t as a coordinate on this moduli space of symplectic structures. Okay. So now I want to use these Gromov-Witten invariants to actually define some algebraic structure which I advertised at on the very first board today. So we're going to define what's called the quantum cup product on cohomology of our manifold with coefficients in lambda naught. So we define the coefficient of gamma in alpha star beta, and it's equal to Gromov-Witten invariant I did put, that's consistent, no, just 0. Okay, so M03 is just a point, and so psi is the only thing it could be, the only non-trivial thing it could be. So we leave that out of the notation. And then this 3-point Gromov-Witten invariant defines the coefficient of gamma in the quantum cut product of alpha with beta. So let me if these alpha and beta are Poincare dual to A and B cycles, we look at the moduli space of J holomorphic spheres with 3 marked points. Looking like this. Okay, so this is a J holomorphic sphere. This marked point is constrained to lie on the cycle B. Similarly, this one here. And this remaining marked point sweeps out a cycle in our moduli space, which we call C. And we weight it by the symplectic area of our sphere. Okay, U is the sphere. Just trying to avoid using beta again. And the Poincare dual to the resulting homology class we get by summing over all these guys is the quantum cut product of alpha with beta. So note that the t to the 0 component counts spheres with 0 energy, which are therefore constant. So we get here, this looks like just this whole thing is a point. So we get points which lie on the intersection of cycles A and B, and then whatever that intersection sweeps out. So that's the intersection product on homology, which is Poincare dual to the usual cup product on cohomology. Okay, so we can say that the quantum cup product is a deformation of the usual cup product over this ring lambda 0. And you know, hence the name quantum cup product, because somehow, you know, morally you think of it as being the intersection product just smeared out by some quantum effects.
Is a sum of, with these kind of t to the lambda coefficients, of usual cohomology classes on M. So my elements alpha and beta reach this series with cohomological coefficients.
Yes.
And can you tell me in those terms what the cup product is? Or have you told me and I don't understand? Because I have summation aj t to the lambda j, where the aj's are in the cohomology.
That's right.
Another one, summation bj t to the uj. Where,
Yes.
Okay. Then their cup product is some other series. Can you tell me what that series is, coefficient by coefficient? Or have you told me?
Yes. What I've told you here is the quantum cup product on generators over lambda naught, right? I mean,
what you said here is take alpha and beta actually to just be classes with integral coefficients and then expand out over powers of t.
yes, yeah. I mean, it's what I've told you is the quantum cup product of classes if alpha and beta are in cohomology of M with rational
So to speak,
coefficients.
For constant elements. Of that
Yes,
field.
yes.
And then when you say the coefficient, you mean that'll be.
We extend lambda naught linearly.
I guess maybe the question is, do the t's multiply the way that we would expect?
Yes, 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 absolutely.
So then the product would be completely determined by the cohomology with q coefficients, where the t's are equal to 0, plus the normal multiplication of t's. Isn't that right? I don't understand.
No.
If you just look at the T0 term, then it's basically you take the usual cup product and
Right.
just take this as coefficients. But then you have, for the positive other things, you count holomorphic curves as well.
But he's asking if it's QT linear.
I mean, formally,
Yes,
the
it's-
cohomology with coefficients in lambda is some sort of a limit of power series with coefficients in the rational cohomology. So you could write a term in this
But-
in terms of coefficients in rational
Right,
cohomology
but
t's.
I mean, the cohomology of M is a finite dimensional Q
I'm
vector
happy
space. So
if you tell me you start with alpha and beta, which are usual cohomology classes,
yes,
and their cup product is a Novikov series.
yes,
And so what you just said was that its constant term is the usual product,
yes,
and then the higher terms are something.
yes.
And can you say what the something is in, just, I don't know, somehow say it again so that, like, what's the t to the lambda coefficient?
T to the lambda coefficient is take the moduli space of all spheres U with omega of U equals lambda.
Ah, okay, that's it.
Right. Yeah, that's this weighting by T to the symplectic area. Okay. Oh, there was another question.
Well, just like, I don't know whether you're about to do this. Can we have an example, like a projective space or something, to keep something?
Sure. I was. Let me state a proposition or theorem or. That this product we've defined is associative, but so that I can. So let me leave the proof of that for next time. And just for this time, let's look at quantum cohomology of CP1. So this has got rank 2. One generator is the identity, and one generator is the Poincare dual to a point class. So I should say, there's another lemma. E is still an identity for the quantum cup product. So
That's true universally.
that's always true, yes. So that tells us all of the quantum cup products except P cup product with P, 2 point classes, quantum cup producted together. So we know that the 0th order term vanishes. What about the next order term? So it should count things that look like this, where these are cycles which are actually our point classes. This is a holomorphic sphere, and we need to see what this thing sweeps out. And of course, I mean, there's one obvious holomorphic CP1 sitting inside CP1, which is the thing itself. So no matter where we choose these 2 point classes, we can choose our marked points, our first and second marked points to lie wherever those guys are. And then we have to look at the space swept out by the possible choices of the third marked point. And of course, the third marked point can go anywhere because, all CP1s with 3 marked points are biholomorphic, no matter where we put it. So what is the space swept out by this remaining marked point? It's the fundamental class of the manifold. So we get is T to the symplectic area of CP1. So let's say we've scaled it, so that's 1, times Poincare joule to the fundamental class, which is the identity. So we have quantum cohomology of CP1 is lambda naught polynomials in P mod P squared equals T. Sorry if that's not visible. More generally, if we take CPN, it turns out that the only homology class of holomorphic spheres that matters for this version of the quantum cup product is lines, and we know there's a unique line through any 2 points. What that ends up giving us is polynomials over lambda naught in P, mod P to the n plus 1 equals T. Sorry? P is in degree 2. Right, yeah. So usually if we put T equals 0, we get the usual cohomology of CPN, just lambda naught of P mod P to the n plus 1. Quantum cohomology adds this extra term T in the fundamental relation in the cohomology of CPN.
Why not twisted cubics?
No, they sorry.
Is there a reason why?
Is there a reason why twisted cubics or other? Yeah, so certainly there are other holomorphic curves in CPN, but you can check basically for degree reasons. Do I still have it? you can check that all higher cohomology classes of curves than just a line would have to contribute to the quantum cut product in a negative degree, basically. Even if you multiplied the two top degree classes together, you would get something in negative degree. So only the lines can contribute. So I think that's at the end of my time. So stop there.
Thank you very much.